this chapter of my PhD deals with the along strike variations of the basement of the Eastern North American margin, and actually the rift system that predated the Central Atlantic Ocean. It was recently published in JGR, and in this talk I will mainly focus on the along strike variation in the width of the Eastern North American volcanic continental margin. And I'll start with a short introduction. Often passive margin are divided into two end members, the Magma-poor margin, which is has a highly complex high offset, low angle, normal faults, and usually described as tend to be or might be quite wide. When I mean wide, I mean the distance between the stretch domain, which is faulted but not thinned, and the oceanic domain. So that might reach up to 350 kilometers in width. The other end member is the volcanic margin, which is characterized by large additions of volcanic and magmatic rocks in the form of seaward dipping reflectors or breakup basalts. And for quite a lot of time, it was thought that volcanic margins tend to be narrow. And I mean, the necking zone from the necking domain between the stretch domain and the igneous domain is usually less than 100 kilometers. And the explanation was either because of fluxes that caused drifting due to hotter than normal mantle would tend to localize strain and creating this sharply necked margin, or that because of the sharp necking for rheological reasons or strain rate, we get this sharply necked margin, sharply necked lithosphere that causes convection. But either way, we would predict to have a relatively narrow margin compared to Magma-poor margin. But indeed, volcanic margins are narrow. For example, the southeast Finland margin has a necking zone of 100 kilometers, as you can see in this section. But other margins, volcanic margins, like the one Gwen was referring to, the Moore margin, could be quite wide. And actually, this section shows more than 300 kilometers, or about 300 kilometers zone of crustal thinning. The way it is usually explained is that, as Gwen said, that rifting was protracted. It took a long to allow the lithosphere to regain its thickness and strength, thus forcing the failed rift to migrate laterally a long time. And the volcanic rifting breakup occurred, it was juxtaposed next to a failed rift. So this hypothesis says that whenever we have very protracted rifting, we would expect to have a wide volcanic margin. And when we would have short, relatively continuous rifting phase that predated volcanic breakup, we will have relatively narrow volcanic continental margin. In order to test this hypothesis, we went to the Eastern North American margin, which is volcanic. And most importantly, it experienced relatively short, that's about 30 million years of rifting, and it was relatively continuous, but most importantly, it was well constrained, well defined due to the numerous work that have been done on the offshore and offshore seen rift strata. So we know it ended it started during the late Triassic, ended in the early Jurassic, and that it followed the Alleghenian orogeny that ended about 270 million years ago, with the accretion of several accreted terrain that constitute the pre-rift basement for the rifting of the Eastern North American margin. And we have two main segments that I will talk on today: the Georges Bank Basin, which is underlaid by the accreted Maguma terrain, which is a sediment-prone, relatively weak felsic terrain, and the Avalon terrain that underlays the Baltimore Canyon Trough here, which is more has a more intermediate composition, which is thought to be speculated to be more resilient to deformation. Rifting ended with the emplacement of the East Coast magmatic province that you can see its geophysical manifestation, which is the East Coast magnetic anomaly that goes all along the margin and correspond both to the continent-ocean transition and to the magmatic additions that were in place during the final stages of rifting. In order to investigate the structure of the margin, we used dense grid of seismic reflection data that was constrained by 40 wells and several refraction lines that crosses the margin. And in order to get better perception of the crustal thickness in some areas, we also use published data of receiver function results. Now let's talk a little bit about the long strike variation of the margin. This is an isopac map that displays the total post-drift sediments of the margin. And we do, when looking at those two segments, the Baltimore Canyon Trough and the Georges Bank Basin, we immediately see that the Baltimore Canyon Trough accumulated much more sediments, up to 18 kilometers of sediments in northern Baltimore Canyon Trough, while the Georges Bank Basin is more moderate and went through probably less subsidence and can accumulate less sediments. To investigate the crustal structure of the margin of the segmentation, let's look at a strike line going from the Georges Bank down south to the Baltimore Canyon Trough, and we'll start looking at the Georges Bank Basin first. So this is the Georges Bank Basin, and we immediately see these beautiful rift basins that are delineated by normal faults, and above them we see this sag basin of Jurassic, Cretaceous, and Tertiary age. If we go further to the west, we see the Long Island platform that separates the Georges Bank Basin from the Baltimore Canyon Trough, which is deeper, has a bigger sag basin, and is underlain by both thin rift and seaward dipping reflectors. And we know the composition of the crust here based on refraction, the published refraction data. What we don't see here, as opposed to the Georges Bank Basin, we don't see as many faults. There probably are faults, but they're probably covered and concealed by the magmatic cover underneath the Baltimore Canyon Trough. And this is how it looks in a structural map. This is the structural map of the top basement. And you can see that in the Georges Bank Basin, we have numerous faults, very complex patterns, but the moderate diffuse depression of the top basement, while in the Baltimore Canyon Trough, we don't see as much faulting, but we do have this deep trough asymmetric that reach up to 8 seconds deep in its deepest part. Next step was to constrain crustal thicknesses along the margin, and for that we used all available data that includes deep seismic reflection and published refraction data and receiver function data. Using that, we were able to constrain MOHO and then crustal thickness. So this is an isopac of the crustal thickness along the margin, and we do see thickness minimum underneath the Baltimore Canyon Trough and the Georges Bank Basin. If we take the gradient of the crustal structure, we clearly can delineate between two domains. The unthinned domain here in blue, we don't see any crustal thickness changes, and the necking domain, which is the domain in which the crust thins towards the continent-ocean boundary, here in yellow, green, and red. And the red line in between them is the hinge line that separates the stretch domain or the unthinned domain from the necking domain. Next step was to map the seaward dipping reflectors, those extrusive basalts, breakup basalts, and the most accurate place to pinpoint them was actually looking at the landward-most extent. And we did this using all available seismic reflection data, and that's allowed the correlation between the seaward dipping reflectors and the East Coast magnetic anomaly. There's a nice correlation in between them. And if we overlay this with the crustal hinge line, we see two different patterns between the Baltimore Canyon Trough, where we see the close relation between the seaward dipping reflectors and the hinge line. That means that the thin domain is almost entirely covered with basalts, while in the Georges Bank Basin, there is a 200-kilometer wide zone that separates the crustal hinge line from the continent-ocean transition and the seaward dipping reflectors. So the necking domain in the Georges Bank Basin is about 200 kilometers, while in the Baltimore Canyon Trough, it moves from 100 kilometers to about 60 kilometers in the southern Baltimore Canyon Trough. So two different styles of rifting and two different relations between magmatism and crustal thinning. If we overlay this...
Sorry to interrupt, this 10 minutes are over, just as a heads up.
Right. If we overlay this map with the crustal terrain boundary, we see that the Georges Bank Basin is underlaid by the Magma, meaning that all the crustal thinning and faulting actually occurred on the Magma terrain, while the Avalon terrain remained intact. We know that there are also no onshore rift basins onshore of the Georges Bank Basin. This is like the Magma took all the strain to itself, as it was the weakest link in the chain, as opposed to the Baltimore Canyon Trough, where we know of famous rift basins, for example, the Newark Basin onshore, but we don't see a lot of faulting going on right east of the hinge line. So to sum it up, let's look at it and at this cartoon of the two segments. One is the Baltimore Canyon Trough, and one is the Georges Bank Basin. So in the Baltimore Canyon Trough, the prairie setting at the end of the orogeny was that the Avalon terrain was juxtaposed on top of old Appalachian terrains, while in the Georges Bank Basin, we had three terrains stacked one upon each other: the Magma, the Avalon, and Gander terrain. Once we start stretching in the Baltimore Canyon Trough, where we have more resilient crust, the formation mostly occur in the reactivation of old Appalachian trusts, forming basins like the Newark Basin or the Connecticut Valley basins, while in the Georges Bank Basin, we don't see any faulting onshore, but we do see a lot of faulting offshore, where the Georges Bank Basin is today. And it is accommodated with crustal thinning, which did not happen during this phase in the Baltimore Canyon Trough. So this is the pre-magmatic rifting, but once rifting becomes more magmatic, strain tend to localize toward the place of final breakup. And what happens in the Baltimore Canyon Trough, it occurs on the Avalon terrain. Strain localizes, and then we start seeing crustal thinning correlated with the magmatic addition at the same location. In the Georges Bank Basin, this occurs right next to the area of thin continental crust, and we get a wide continental margin next to a zone of seaward dipping reflectors and oceanic crust, while in the Baltimore Canyon Trough, thinning is limited to the place of magma-assisted rifting and magmatic additions. So to conclude, the Baltimore Canyon Trough is a narrow volcanic margin with 50 to 80 kilometers of necking zone. The Georges Bank exhibits a broad 200-kilometer zone of thinning. And this is the main point of the stop. Pre-magmatic thinning determine the widths of the future volcanic margin. We propose that the cause for the variation in pre-magmatic thinning is actually the heterogeneous prerift rheology of the lithosphere, specifically the differences in strength between the Avalon and Magma terrain. Thank you very much.
Excellent. Thanks a lot. There's time for one or two questions, and we have one question already. Leanne?
Hello, thank you. That was a great talk. I'm interested in just going back to how you identified the continental material associated with the Baltimore Canyon Trough underlying the Central Atlantic area there as Avalonia. Thank you.
Yes, so it's basically based on previous publication by Hatcher et al. And I think what they do know is actually what's going on onshore. Getting to know exactly, no one could actually sample this data, but they do have some well in the Salisbury embayment, which they identified as Avalon terrain, and they basically, based on geophysical data, extrapolated it to the offshore.
Okay, and another question, Mohammed.
Hi, thanks, Sasha. Thanks, Guy, for the excellent talk. I was wondering, in your definition of the narrowness of the margin, especially the Baltimore Canyon transect, you mentioned that it's narrow transect, but if you look at the conjugate side, you have much wider, actually, continental crust, and you have on the African side, you have very wide basins there, actually, that tells you that you have actually like a little bit wider continental crust than on the American side.
So are you referring to the Gila transect?
Yeah, so if you look at the Dakhla transect, actually, you have a whole onshore basin, actually, with a lot of synrift structures there. And if you look at the seismic refraction that has been done on that side, they seem to hint, actually, that you have much more crystal thinning, actually, than on the conjugate side. So basically, if you take both sides, like the margin is not as narrow as it appears on the American side.
So if I remember right, the southernmost, the Gila transect, that actually is the conjugate for the Baltimore Canyon Trough, isn't that wide. What's the wider transects are the one further to the north that are the conjugate of Nova Scotia. There's no conjugate for the Georges Bank Basin, but actually the southernmost one, which they termed the conjugate of Baltimore Canyon Trough, if I remember correctly, is actually quite narrow as well. You don't have a lot of magmatic addition. You do have some, but basically the necking is, if I remember right, is quite narrow. But we can check it out afterwards if you like.
Yeah. Okay, thanks.
Yeah, actually, we're kind of running out of time, but that question by E. Chen is so interesting that we have to discuss it again. Could you unmute and ask yourself?
Yeah, I'd like to ask about the geological properties of each domain. I wonder if you have some quantitative estimates on that. For example, viscosity, yield strength, something like that.
That's a great point. We do not have that, actually. We have actually descriptions of those domains coming from the onshore. And we know we have one sample of the Meguma in the Georges Bank Basin that is supposed to be a meta-sediment, while the Avalon terrain is supposed to be more intermediate island arc kind of crust. But in a quantitative manner, I cannot, I didn't find actually any quantitative knowledge about the rheology of each one, but we would presume that the felsier and more sediment prone would be weaker and more prone to deformation.